Now we will see one more application of Banach contraction theorem. Not only Banach contraction theorem, but we will see the application of the theorem 6.1.3, and again this one, where X is your compact metric space, T is a contractive map, then we have a fixed point. So we will see the application of this. So here is the application of fixed point theory in the integral equation. So let us take x is equal to c a b, set of all continuous real valued functions defined on the closed interval a b with the uniform matrix. Uniform matrix means with respect to the sup metric. And let k be a continuous function defined on the closed interval a b cross closed interval a b, and let phi be a continuous function defined on the closed interval a b. Now consider the equation f of x is equal to phi x plus lambda times integral a to x k x y f of y dy for all x in the closed interval a b, where lambda is a parameter. This equation is called Volta equation. Now we will see that this Volta equation has a unique fixed point. So for any lambda in R, the Volta equation this has a unique solution f that is continuous on the closed interval AB. Okay. So for this again we will have to prove that this is nothing but the solution of this is nothing but it is a fixed point of some mapping. So first we will have to define a mapping. So since K is continuous on a compact set, this one, so it is well defined because the K is continuous on the compact set, so maxima and minima exist, so it is well defined, and therefore there exists a constant K greater than 0 such that mod of Kxy is less than or equal to 0, because K is a continuous function, so defined on a compact set, so it must be bounded. So this is what. Now define the transformation T from f to T of x on x by this word. T of f of x is equal to phi x plus lambda times this a to x k x y f of y d of y for all x. Okay, and now we will prove that this T, okay, satisfy the condition of theorem 6.1.3. So for all x, y, z we have mod of T f of x minus T g of x is equal to mod of lambda times a to x k x y mod of f y minus g y dy. Okay, and this is less than or equal to mod lambda x k times x minus a d f j. Okay, why it is d f j? Because we are considering the d f j is equal to the supremum of x in AB mod of f of x minus f of y. So we are considering the supremum of this one. So this is less than or equal to. Now we can operate t square. So t square f of x minus t square g is equal to t of f of x. So we can operate both the sides. So we can write it this way, and therefore t square f of x t square g of x is equal to this one, and now we can simplify, we will get this one. So here is this one. Continue in this one, again you operate t over here, we will get continue in this way, so operate n times, so we will get this is less than or equal to this one. It means what? It means that t and f minus t and g is less than or equal to mod of lambda k b minus n whole raised to the power n divided by norm factorial n dfg. Okay, so this so as recall that this term Rn upon factorial n converges to 0 as n tends to infinity. We conclude that there exists n such that Tn is a contraction map. So this is less than or this is sticky less than 1 but greater than 0. So Tn is a contraction map. Taking n sufficiently large, so this is less than. No. Here is we have to prove that. So then there exists Then by using a theorem then by using this 6.1.2, it is not 6 point. So this is 6.1.2. So by using 6.1.2, so here is this theorem 6.1.2, not 3. So here is 6.1.2. There exists a unique solution f satisfying that T of f is equal to f. Obviously, if T of f is equal to f, then f satisfies this integral equation. So this is the the application of the fixed point result. Now we have a corollary. We say that if K is a mapping from the closed interval AB cross AB to R and phi is a continuous mapping on the closed interval AB, then there exists a constant epsilon greater than 0 such that for any lambda in the open interval minus epsilon to epsilon, there is a unique solution f of x, okay, which is a continuous real valued function defined on the closed interval AB of the unique solution of the integral equation, this one. And this you can prove by using the result 6 point by using this mapping. So by using this mapping, we can get the result here is. Okay. So now I stop over here, and this I am completing the fixed point theory chapter. Okay, where we have discussed in this chapter we have discussed so first of all we have discussed the definition of the fixed point, and then the contraction mapping, Lipschitz mapping, contractive mapping, non-expansive mapping, they are examples, and we have seen that the proof of the Banach contraction theorem and statement of the Banach contraction theorem, and Banach contraction theorem, the proof of the Banach contraction theorem is by using the proof of the Banach contraction theorem, we can also calculate a fixed point. And then we have seen that if the set, the underlying set is compact and the metric, the mapping is T is your contractive map, then even then it has a fixed point. And then we have seen 3 different applications. For number 1, the application to the linear system of equations, and then the applications to the ordinary differential equation with initial condition, and third we have seen the applications of fixed point results to integral, Volta integral equation or integral equation. So this is I am closing this talk over here. Thank you very much. Okay, welcome you all in this last talk of this course of metric spaces, where we will discuss some miscellaneous results which we have used in our previous talks. So there are some very simple things which I have mentioned as an appendix. So we can write an appendix chapter A, chapter B, chapter C, and so on and so forth. So some basic inequalities, you can see all these basic inequalities you have already discussed or proved in your earlier classes. So for any alpha is greater than 0, the function f of x defined as x upon 1 plus x is monotonically increasing. This is you can prove very simple way, that you can consider y is greater than x and x is greater than or equal to 0, then we can write 1 upon 1 plus y is strictly less than 1 over 1 plus x. And so you can take 1 minus 1 over 1 plus y is greater than or equal to 1 minus 1 over 1 plus y. And just you solve it, you will get this one. And it means what? It means that because y is strictly greater than x, so this is strictly greater, so it means that this function is monotonically increasing. Okay, so very simple one. Similarly, you can see that if a, x and y are two real numbers, then this inequality holds good. And this you can prove very easily. Let x and y have the same sign, then without loss of generality, we may assume that x is greater than 0, y is greater than 0. Then this is because both are non-negative. Okay, so this is equal to this one. Okay, and therefore this you can write simply in this way, and this is less than or equal to this term plus this term, and then you can take it is equal to the mod of this and then mod of this one. And if they have different sign, then we may assume that mod of x is greater than y, then mod of x plus y is less than or equal to mod of x. And again, by the previous proposition where we have proved that this function is 1 over 1 plus x, we have proved that the function x upon 1 plus x is monotonically increasing, and here is mod of x plus y is less than mod of x. That function is monotonically increasing. By using this function, we will get this one, and therefore this is holds good. So this is very simple one. Now, here is the important thing is that it is important to note that we have the Holder inequality. So Holder inequality, we used the Holder inequality to prove that the metric space LP or Rn are the metric spaces. We use the Holder inequality and Minkowskian inequality. So in the Holder inequality, let xi and yi are greater than or equal to 0, p is greater than 1, q is greater than such that 1 over p plus 1 over q is equal to 1. Then the summation I runs from 1 to n xi yi is less than or equal to summation I runs from 1 to n xi p whole raised to the power 1 over p summation I runs from 1 to n yi q raised to the power q whole raised to the power 1 over q. Okay, and when p q is equal to 2, we have this kind of inequality, and it is called the Cauchy-Schwarz inequality. The second is we have the Minkowskian inequality. So Minkowskian inequality we have here is this xi is greater than 0, yi is greater than 0, and this summation I runs from 1 to n xi plus yi raised to the power p whole raised to the power 1 over p. This is less than or equal to summation I runs from 1 to n xi p whole raised to the power 1 over p plus summation I runs from 1 to n yi p whole raised to the power p. Okay. So this you can prove. If p is equal to 0, then there is nothing to prove. So we assume that p is greater than 0. Note that this is equal to this term plus this term, and let q is greater than 1 such that the 1 over p plus 1 over q 1, and then from here we can, and by using the Holder inequality, we can write this term is equal to this one, and if this is equal to 0, then again this holds good, and if this is not equal to 0, then by dividing this inequality by this, we obtain this result. So this is very simple. The thing is, and that's why I have mentioned all these inequalities in the appendix. Now we have in the previous year we are taking the summation from I runs from 1 to n, that is to the finite sums. Here is the finite sum. So the next result is for infinite sums. So here is we have x and y and b sequences or non-negative terms such that this series and this series are convergent. These two series are convergent, then this series is convergent, and not only this, this term is less than or equal to this plus this one. So this you can take by using the previous theorem. So for any positive integer from the previous theorem, we can write this is less than or equal to this one. Now since this is an increasing sequence of non-negative real, it is bounded above, so the sum this is, it follows that this is convergent and that this holds good. So this is very simple by using the previous result. Now, if P is greater than 1 and alpha is greater than 0, A is greater than 0 and B is greater than 0, then we have A plus B raised to the power P is less than or equal to 2 raised to the power P minus 1 A raised to the power P plus B raised to the power P. This you can prove very easily. If either A or B is 0, then nothing to prove. Suppose that A is strictly greater than 0 and B is strictly greater than 0. Since the function xp defined on the set of all positive numbers is convex, okay, when p is greater than 0, we have this inequality which is equivalent to this one. Here is we are using the convexity of the function. So I think you have studied the definition of the convex function in your class 11 or somewhere. Then I gather here in this second chapter of the appendix upper and lower bound. So let A be a subset of R. Okay, we say that capital M is a real number, is an upper bound of A if x is less than or equal to M for all x in A. Small m, a real number, is called a lower bound of A if M is less than or equal to x for all x is in A. A is called bounded from above if there exists an upper bound of A, and A is called bounded below if there exists a lower bound of A. It is called bounded if upper bound and lower bound both exist. Now, if A has an upper bound M or lower bound small m, then A may have many upper bound or lower bounds, namely all numbers greater than, okay, greater than or equal to capital M is an upper bound. Okay, so let A be a subset of R, then a number capital M is said to be a supremum or least upper bound of A. If M is an upper bound of A and M is less than or equal to M dash for all upper bounds of M. That is to say, M is the least number among all upper bounds. Similarly, a small m is called infimum or greatest lower bound if small m is the greatest number among all the lower bounds. So, the supremum and infimum of A are denoted by sup of A and infimum of A respectively. Note that the supremum and infimum are unique if they exist. Also, the supremum and infimum of a set may not lie in the set. For example, the set A consists of all rational numbers which are strictly less than under root 2. Okay, is bounded from above by under root 2, but under root 2 has no supremum in Q, but under root 2 is not in Q. Okay, if A does not have an upper bound, then we define the supremum of A is equal to infinity, and similarly if A does not have a lower bound, then we define infimum of A is equal to minus infinity. By convention, we say that the infimum of empty set is equal to minus infinity, supremum of infinity set is equal to minus infinity, and infimum of empty set is equal to minus infinity. By the supremum of a set belongs to it, then if the supremum of a set belongs to it, then A is called the maximum of A. Now, let xn be an arbitrary sequence of real number. We construct a new sequence yn by taking the supremum or successive truncated tails of the original sequence yn. How we can do? We can take yn is equal to supremum of xk such that k is greater than n. The sequence yn is monotonically decreasing, and the supremum is taken over smaller value. Therefore, the sequence yn has a limit. Such a limit is called limit superior of the sequence xn, and it is denoted by limit superior. Similarly, by taking the infimum of successive truncated tails of the original sequence, okay, this one, then we get a monotonically increasing sequence yn. The limit of that sequence is called limit infimum of xn, and it is denoted by limit infimum. We have the definition that xn be a sequence, then limit superior of xn is equal to, you take the limit as n tends to infinity. So first you take the superior of xn when k is greater than n, and then you take the limit as n tends to infinity. Similarly, you can define the limit inferior. Of course, the limit inferior of a sequence is always less than or equal to the limit superior of the sequence xn. And the sequence xn converges if and only if limit superior and limit inferior are equivalent. Now, if we consider xn is equal to minus 1 raised to the power n, then the limit inferior of this sequence is equal to minus 1, and the limit superior of this sequence is equal to 1. And therefore, the limit inferior and limit superior are not equivalent, and so you can see that the sequence xn, which is defined as minus 1 raised to the power n, is not a convergent sequence. Now we have another appendix, that is chapter 3, where we have discussed partial ordering. Okay, so partial ordering is that a binary relation this on a non-empty set X is called partial ordering if the following condition holds good. Number one is A is related to itself, it is called reflexive. If A is related to B and B is related to A, then A must be equal to A, it is called antisymmetric. If A is related to B and B is related to C, then A is related to C, it is called transitivity. The partial order, a non-empty set X is called partial order if there is a partial ordering on X. The word partial emphasizes that X may contain elements A and B for which neither A is related to B nor B is related to A whole. In this case, A and B are called incomparable elements. So, if A is related to B or B is related to A or both, then A and B are called comparable elements. The totally ordered set, a partially ordered set X is said to be totally ordered if every two elements of X are comparable. In other words, the partially ordered set is totally ordered if it has no incomparable elements. And then we have a definition. So let M be a subset of a partially ordered set X. Then the element X is called upper bound. Okay. If X A is related to X for all element X in M, and X is called lower bound if X is related to A for all A is in M, and X is called maximal element if X is related to A implies X is equal to A. Then a subset of a partially ordered set M may or may not have any upper or lower bound. Also, M may or may not have maximal element. Note that a maximal element need not be an upper bound. Then, for example, we consider here is let X be a set of all real numbers and let A is less than B have its usual meaning. Okay. Then X is totally ordered and it has no maximal element. If X is equal to set of integers, okay, set of natural numbers, and we define the ordering like this, M is related to N, means M divides N. Okay, then this relation is a partial ordering on X. Now consider Px power set of all subsets of X. So X is related to B means A is a subset of B. Okay, then the set Px is a partially ordered set and the only maximum element of Px is the whole space X. If let X be the set of all ordered n tuples, X is equal to x1, x2, xn, y is equal to y2, y1, y2, yn of real numbers, and let X is related to y, means xi is less than or equal to y for all I, then this relation is a partially ordering on X. And now finally we have the Zoun's lemma, which says that let X be a non-empty partially ordered set in which every totally ordered set has an upper bound. Okay, then X has at least one maximal element. So we use this partially Zoun's lemma in some result. And then in the beginning, I have defined, I have mentioned that Cantor intersection, or this is finite intersection property, and then the characterization of a compact set. So finite intersection property we have defined. That result was basically motivated by the nested interval property. So if A is a set of real number bounded from F, then A has at least one upper bound. Okay, this is called the least upper bound. So if I is equal to interval, closed interval A1, B1, I2 is equal to A2, B2, and so on, be a sequence of nested, closed and bounded interval. Nested closed means that A1 contains A2, I1 contains I2, I2 contains I3, and so on. Then there exists at least one point common to every interval, that is to say the intersection of this is non-empty. What we have proved in the finite intersection property, that if we have a sequence of non-empty closed subsets of a complete metric space, okay, and this is a decreasing sequence, okay, and whose diameter converges to 0, then the intersection contains only one element or it is not. So that theorem was inspired by this nested interval property. Okay, so just I want to mention this nested interval property for you here is. Okay, here you can see that in the nested interval property, if we consider, as I also mentioned in the finite intersection property, the closeness is very important. Also in the nested interval property, the closed interval, the closeness is also important. So if we consider A1 open interval, closed interval 0, 1, and A2 is this and so on, then AN is a sequence of open closed interval. It is clear that the sequence AN is nested, that is A1 contains A2 and so on, but the intersection of interval is empty. This is equal to empty. So it means that the closeness of the intervals must be important, and this we have also seen in the case of finite intersection property, where the closeness is also very important. Also, we can see that AN sequence of closed infinite intervals. Okay, infinite intervals. So you can see that because there we have proved the diameter of the set converges to 0. Okay, so here is the diameter of the set converges to 0. So and this then so we have this is a sequence of closed intervals, and of course it is nested interval property holds, but the sequence of interval is nested, but the intersection is non-empty because the diameter converges to infinity. And then finally we have the Horn-Borel theorem, which says that every closed and bounded interval of the real line is compact. So this is the proof of the theorem, but I am not going to prove because I just mentioned it because we use the Horn-Borel theorem. Then finally, I just would like to mention the Cantor set, because we have mentioned that the closeness, we have seen the openness, the limit point, interior point of the Cantor set. So what is the Cantor set basically? So counter set, so let us take C naught is the closed interval 0, 1. So here is you have, suppose this is your closed interval 0, 1, including the endpoint. Okay. Now you divide this closed interval into 3 parts. Okay. So you divide into 3 part and remove the middle part. Okay. Then what you will get? You will get C1. C1 is 0 to 1 over 3 and 2 over 3 to 1 close interval. So C1 is equal to close interval 0, 1 over 3 union close interval 2 over 3, 1. So this one. And then again you divide this close interval into 3 parts. So here you will get 1 over 9 and here you will get 2 over 9. Okay. Similarly, you can divide this into 3 parts. Okay. And remove the middle part. And then you will get this one and this one. And here you will get this one and this. And take the union of this. That is equal to C2. Okay. Continue in this way. Okay. So continue in this way. We get a sequence Cn of sets where Cn is obtained from Cn minus 1 by removing the open middle third of the 2 raised to the power n minus 1 term. So disjoint intervals of which Cn minus 1 is composed of, that is Cn is equal to Cn minus 1 in this one. Then the intersection of all this one, which is called C, and this C is called intersection of all Cn is called the Cantor set. Okay, so this is the definition of the Cantor set which we have used, and now we have also given here prove that the Cantor set is compact. Okay, so basically you will have to prove it by using the Horn-Borel theorem. So since each En is the union of 2 raised to the power n disjoint closed interval, so that each Cn is closed. Also, arbitrary intersection of closed set is closed, and so this set is closed, and this set is also bounded, and this set is closed and bounded subset of the closed interval AB. So by Horn-Borel theorem, C is compact. So this way you can prove the compactness of this one. And now we have some miscellaneous results, and that is let f be a function defined from the closed interval 0, 1 to R, continuous function, such that f of x is greater than or equal to 0 for all x in the closed interval 0, 1. Then the integral from 0 to 1 f of x dx is equal to 0 if and only if f of x is equal to 0 for all x in the closed interval 0, 1. Now, if f is a function from the closed interval 0, 1 to R is non-negative and Riemannian integral on the closed interval 0 such that the integral from 0 to 1 f of x dx is equal to 0, then we cannot conclude that f is a 0 function on the closed interval 0. For example, we can consider f of x is equal to 0 if x is not equal to half, it is equal to 2 if x is equal to half. Then f is Riemannian integrable on the closed interval 0, 1, and the integral from 0 to 1 f of x dx is equal to 0. Here is the Young's inequality. So Young's inequality that if a and b are non-negative real numbers, p is greater than 1 and q be such that 1 over p plus 1 over q is equal to 1, then ab is less than or equal to a raised to the power p divided by p plus b raised to the power q divided by q. And this here the inequality holds good if a raised to the power p is equal to b raised to the power p. And now finally we have the Weierstrass theorem. We say that let f be a continuous function, then there exists a sequence of polynomials of real coefficient that converges uniformly to f. Okay, so for every continuous function we can every polynomial can be approximated by means of a polynomial function. Okay, so that is the end of this course. So here I have presented some miscellaneous results, some miscellaneous definitions which we have used in our lectures. So here I complete this course. So thank you very much for attending this course on metric spaces. I hope that you enjoyed this course very well, and definitely it will be very helpful to all of you. As I mentioned in my beginning uh, talk, that the course of metric space is the foundation of the course of functional analysis. So if you want to continue your mathematics in the analysis, especially on the functional analysis, you must be very good in your course of metric spaces. Of course, this course of metric spaces will also helpful to study the topology, the course of topology. So thank you very much once again for offering this course and for joining this course. And I hope once again you enjoyed this course very well. Thank you very much.